Okay, so so far we have so far we have done the electromagnetic spectrum, right? And the electromagnetic spectrum is the whole spectrum of the electromagnetic wave. Okay, so visible lights out of this spectrum, visible light makes small portion of that electromagnetic spectrum, because if you see that the visible light that is in the small range, and lots of other wavelengths and frequencies belongs to the another than the visible light. Okay, now let's see that what are they. Look, um, in the electromagnetic spectrum, that whole spectrum belongs to, first of all, let's start from the broadband wireless radio waves. Okay, that have the longest wavelength. Okay, if you see that here, the wavelength of is that is about um, 10 to the power 3. See, 10 to the power 3, and about 10 to the power 2, 10 to the power 1, 10 to the power 0 meter, yeah, 10 to the power 0 meter to 10 to the power 3, a kilometer, that much long, the radio waves. And if you think about the microwaves, and the microwaves are, you see that the microwaves are um, so the microwaves are um, about 10 to the power minus 3 to 10 to the power minus 1 meter. Okay, so if you think about the terahertz, the terahertz belongs to about 10 to the power minus 5 to 10 to the power minus 4 meter. Infrared, then comes infrared, that is about 10 to the power minus 6 to 10 to the power minus 5 meter. And then the visible light is tiny here. If you see that, the tiny bit here, okay, that is about 10 to the power minus 6 to 10 to the power minus 7 meter, or so that is the wavelength of that, about couple of hundred or 300 to 700 nanometer. That is, because you can convert that to the nanometer, that is about like that. So ultraviolet is about 1 nanometer. See, ultraviolet is about 1 nanometer, and the infrared, the visible light is about the 300 to 700 nanometer, if you see that. And X-ray has even smaller wavelength, 10 to the power minus 10 meter. Gamma rays is about 10 to the power minus 12 nanometer, right? And these are some examples, right? AM radio, cell phone, and then radar has this range, wireless has this range, microwave oven has this range, and like that. Night vision has about infrared. Night vision, you have seen, that's the infrared, right? And this is the UV, ultraviolet, X-ray things. So look at that here. Wavelength is decreases. If the wavelength decreases, if you see that wavelength decreases, so let me take that. So wavelength decreases. So this is the relation, okay, energy and the wavelength. Here the nu is the wavelength, okay. So nu is the frequency, and c is the velocity of light, and lambda is the wavelength. So what is happening, if wavelength increases, larger the wavelength, smaller is the frequency, right? Larger the wavelength, smaller is the frequency, because the wavelength is in the denominator, right? So because c is constant, this is c equals to this one, 2.998 times 10 to the power 8 meter per second in the vacuum. That's why velocity of light, this is velocity of light, that's why it is a constant. So this is a constant value. The frequency is um, just the c by lambda. It means the inversely proportional to the the wavelength. So if the wavelength increases, frequency decreases. Look at that. This is the frequency. As the wavelength decreases, wavelength is become smaller and smaller, and then you have a frequency is more and more. And what happens if you have a frequency? So energy is equals to h nu. Okay, and h is the Planck's constant and nu is the frequency. Oh, okay, it means that if frequency increases, this frequency increases means energy also increases. So that's why look at that, X-ray has 10 to the minus 10, gamma ray has 10 to the power minus 12. That much small wavelength, it means that it has a huge frequency, more energy. That's why these electromagnetic radiation, gamma ray, X-ray, ultraviolet even also, they can ionize our biological components. So that's why they can do the cell mutation. That's why they can create the cancer. They are dangerous. That's the reason, because they have a very high energy, and their energy is sufficient to manipulate your DNA, RNA structure. So that's why they have the high frequency. Okay, this is the electromagnetic radiation. Now let's take in one example. So let me take that down. Okay, a sodium street light given off yellow light that has a wavelength of 589 nanometer. Right, 589 means 300, let's say 60 to 700 nanometer. That is the visible. Okay, visible means you have 7 color in the visible light. Okay, so this is, and what is the frequency of this light? This is the formula. So frequency is equals to, frequency nu is equals to velocity of light divided by lambda, and that is equals to velocity of light is 2.99 times 10 to the power 8 meter per second, divided by lambda is this much nanometer, right? This much nanometer means 589 nanometer. That is equals to, this is meter, this is nanometer. That's why you can convert nanometer into the meter, right? And that is 2.99 times 10 to the power 9 times 10 to the power 8 meter, divided by 589 times nanometer means 10 to the power minus 9 meter, right? 10 to the power minus 9, that is meter, and it has second also. So meter cancels, and its value is this. So this is the value. That's why. Okay, see, that is conversion. It's 2.99 times 10 to the 8 divided by 589 times 10 to the power minus 9, right? This is the minus 9. That's why this guy write this up. Okay, it's the same thing. Is equals to 5.09 times 10 to the power 14 per second. Means that 5.09 times 10 to the power 14 hertz, right? So hertz. So hertz means per second. So this must very high frequency. Okay, that's the frequency of this light in the spectrum. So now let's go to other a very nice important fact, that is the black body radiation. Okay, so a black body is that which can emit the light if you give that heat. So sunlight consists of a range of broadly distribution wavelength that forms a continuous spectrum. We know that. A black body is convenient ideal emitter of that approximate that the behavior of many material when heated. It means that black body is that which can emit light when heated, and it can emit many spectrum of the light. It's not only the white light. Okay, it can produce many type of the lights. That body, that is the black body. For example, if you heat that, it will produce the light. Okay, so a good approximation of black body that can be used to observe the black body radiation. So how do you observe the black body? Because it absorbs all the lights. Okay, black body means that can absorb light. That's the black body. Now, how do we know that? We will find that what kind of the radiation that black body is giving at a particular temperature. That way we can see the black body. Okay, now let's see that one very nice So let's see this. Okay, now what happens to the black body? What actually the black body is? Now let's see that here. Okay, look, this is the black body. At the low temperature, it's almost black because it's absorbing all the light. If you give little bit heat, it will have this color. More heat, this color. More heat, this color. More heat, yellow. More heat, green. More heat, blue. More heat than this light purple. Then more heat, this violet. And then this is the X-ray. This high heat. If you give the high heat to the black body, it will give you X-ray, gamma ray. So all kind of the spectrum black body can give at a particular temperature. Okay, so now let's see here spectral irradiance. Okay, so this is the wavelength, and now let's see at the 50. So at particular temperature 50 degrees centigrade, this is the black body spectrum. So let's say this is the this light is the sunlight at the top of the atmosphere, and this is the approximation of the black body. See, black body, this is the wavelength. So spectral irradiance at 0, about the 10, it is 250 nanometer, and 500 nanometer you have this is the visible range, right? 500 to 700, this is the visible range. You can see the sunlight at the top of the atmosphere, and all others wavelength it can give you. Okay, so this is the black body spectrum at 5250 degrees centigrade. So this sort of the light it will produce at this degree centigrade, and the highest is the peak, right? This is about 600 nanometer wavelength light it will produce at 5 to 50 degrees centigrade. That's the maximum irradiance that is. But these are also, but they will look visible because they don't have the more energy, watt per meter square per nanometer, right? This is the spectral irradiance is less. So this is the black body. So now let's see that black body radiation and the ultraviolet catastrophe. Okay, so the maxima in the black body curve lambda max is shifted to the shorter wavelength as the temperature increases. So if the temperature increases, look at that, the temperature increasing, so wavelength is decreasing. Look at that, 2500 Kelvin. This is your wavelength is here. So this is the wavelength. Okay, and at 3400 Kelvin, this is the wavelength. Wavelength is decreasing, right? And 4400 even it is decreasing, right? Only this much. And 5500 it is decreasing. Oh, sorry, 5500 it is decreasing like that. See, wavelength is decreasing as the temperature increases. The peak wavelength is decreasing, temperature increases. Okay. The theoretical expression as function of temperature fit the observed experimental blackbody curve, while at the longer wavelength, yeah, theory and the experiment for the longer wavelength it fits. And but there were significant discrepancies at the shorter wavelength. For longer wavelength, yes, but the shorter wavelength, if you go to the classically, there is the discrepancies. Okay, it will give the very high frequency. So shorter wavelength there are discrepancies, and that discrepancies is said to be the ultraviolet catastrophe. So now the previous picture is the same. This is the wavelength. These are the temperatures. See that temperature increases, wavelength is shifted to the smaller one. So this is in y-axis power and x-axis wavelength. Okay, so now the Planck's constant, because the last time we are reading the Planck's constant also. So see, Planck had assumed that the vibrating atoms required a quantized energy, which he was unable to explain, right? Energy should be quantized, right? Energy equals to N times Planck's constant times nu. Nu is the frequency, and this NH is the Planck's constant, and E is the energy. So the vibrating atoms required a quantized energy. These are the energy for the vibrating atoms. This is the energy for vibrating atoms. Okay, the quantity H is the Planck's constant. Then finally later on the constant is found, this value 6.626 times 10 to the power minus 3 joule times second. This is the Planck's constant. Okay, so now let's discuss a little bit more about the photoelectric effect. Okay, so what is the photoelectric effect? The Albert Einstein observed this photoelectric effect, and he got, I think, a Nobel Prize for this also. And it had been observed that the electron could be ejected from the surface. So photoelectric effect says that electron could be ejected from the surface of the metal. Okay, the light had to have frequency greater than some threshold frequency. Surprisingly, the kinetic energy of the ejected electron did not depend upon the brightness of the light, but increased with the increasing frequency of the light. It means that if this is a metal surface and here are the electrons, if you heat that metal surface with the light, then the electron will jump. Okay, electron will jump, or electron will ejected out from the surface. That is the photoelectric effect. Photo means the light, electric means the jumping the electron, photoelectric effect. Okay, so what happens? Light had to have the frequency greater than some threshold frequency. There should be some threshold frequency, but every light cannot eject the electron, but that wavelength light can eject the electron which cross some frequency threshold. Okay, so surprisingly, the kinetic energy of the ejected electron did not depend upon the brightness of the light. How intense is the light? It doesn't depend, but it depends upon the frequency of the light. Okay, so that's the photoelectric effect. Here is the one example. Look at that. 700 nanometer, no ejected. You didn't get any ejection because you know that you should have some threshold frequency. You have to cross that threshold of the frequency. Look at that. 700 nanometer, you give the 700 nanometer wavelength, no ejection, but you decrease the wavelength. Decreasing the wavelength means increasing the energy of the wave. Okay, wave means the light. Okay, you are decreasing the wavelength from 700 to 500 nanometer, then you are able to eject the electron. And with the velocity is this. Vmax is velocity of that ejected electron is 2.96 times 10 to the power 5 meter per second. Yes, you cross the threshold. That's why 400 nanometer also increase, and 200 nanometer also will increase. And you see that 500 nanometer. So because the energy equals to h nu, and 500 nanometer and the equals to the h nu equal to c by lambda, right? So that's why smaller is the lambda. See, smaller is the lambda, more is the velocity, because you have the more energy, right? Because the lambda is in the denominator. As the wavelength decreases, energy will increase, right? Because the lambda is in the denominator. That's why a smaller number in the denominator give you larger number altogether, right? So that's why look at that. 500 nanometers. This is the 2.96 10 to the power 5 meter per second, but the 400 nanometer 6.22, right? It's increased. So that's the photoelectric field. Okay. So now again, the energy of the photons depend upon their frequency, right? Last time also we see that E is equals to energy equals to h nu. H is the Planck's constant, or nu is equals to c by lambda. So that's why nu equal to c by lambda. That's why energy equals to h c by lambda. This is the constant. This velocity of light, this is also constant. That's why this is on constant. And if you know the lambda, you can find out the energy. Done. So again, electrons were ejected when hit by photons having sufficient energy, right? Last time we see that. So that's why what happens is electron is wave also, and electron is particle also. And similarly, light also particle as well as wave. Okay, because the light can interference, light can have the interference polarization. That's why it is wave. And light can eject the electron. That's why it behaves as like a particle. That's why light has wave particle duality. Duality means it is both. It is wave also, it is particle also. Why it is wave? Wave, because why it is wave? Why wave? Why light is wave? Because it can have interference, polarization, and diffraction. Why it is particle? Because it can cause photoelectric effect. So it can, light can show the photoelectric effect. That's why it is particle. It can have all property of the wave. That's why it is wave. So that's why, yes, light has the both property of the particles also, property of the wave also. So that's why this is the light has wave particle duality. Okay. So now let's take one example. Okay. So when we see the light from the neon sign, we are observing radiation from the excited neon atoms. If this radiation has the wavelength 640 nanometer, what is the energy of the photon being emitted? Very easy, right? So what is the energy? Energy equals to, we discussed last time, energy equals to hc by lambda. This is the value of h. This is the value of c. This is the lambda. Lambda is in the nanometer. That's why we convert it into the meter. That's it. So E equal to h. H means 6.hc by lambda equal to h is 6.626 times 10 to the power minus 34 joule into second. Okay, and c is 2.998 times 10 to the power 8 meter per second divided by 640 nanometer. But 1 nanometer has 10 to the power minus 9 meter, right? 1 meter has 10 to the power 9 nanometers. So 1 meter has 10 to the power 9 nanometers. So nanometer cancel, and when you calculate these all using the calculator, then E equals to this value, 3.110 times 10 to the power minus 19 joule. This is one example, pretty. Okay. So now let's see the hydrogen atom, hydrogen spectrum lines. Okay. So what happens to the hydrogen? So hydrogen has one electron. So if you give the energy to the hydrogen, it will jump up to the another level. Okay. So now let me check one. So now let's take hydrogens. Okay. So this is the nucleus. Hydrogen has one proton, no neutron, right? This is first cell of the atom. This is the second energy level, you can say, of the atom. This is third, like that. And here is one electron, okay? This is the electron, negatively charged. So if you give the energy, this is the energy to this electron, that will go to this. You further give you, then that can go to the this. And if you have outer also, so it can go further, right? So once you give the energy to the electron, it will jump either this one, or it will either jump to the second level, or either jump to the third level, and like that. Okay. So and once it get the energy, it jump to the upper level. These are said to be the upper level. Okay, this is the proton, this is the electron here. Let's say electron here. Okay, so let's say electron here, and that is jump here. That's the upper level. That is jumping here. That is jumping here. Once you give more energy, that will jump more. Okay, so after jumping, what will happen? It will start returning back instantly, about within 10 to the power minus 15 seconds, for example. It returns back. It returns back here, and this also can returns back to this. Okay, this also can return back to this, like that. Okay, or this can return only to that. That can also return only to that. So either the jumping of the electron from this energy level to the first energy level, that can happen, or to the second level, or to the third level, like that. And when that the electron jump back, if electron so what happens is, when energy is given to electron, it jumps to upper energy level. It jumps to upper energy level. Okay, so after that electron jump back to ground state. This smallest energy level, the smallest energy level is said to be ground state, which is the smallest energy level. Then other energy levels are said to be the excited state. They are excited. Okay, so the smallest energy level, the energy level where the electron has the smallest energy, that is the ground state. And if you go to the another level, those all another levels are the excited state. So this is the first excited state, this is the second excited state, that will be third excited state, like that. Okay, so when they jump back to the ground state from the excited state, right? The energy, upper energy level means upper energy level called excited state. Okay, so jump back to the ground state from the excited state, it emits radiation. So when it jump back, whatever the energy it has taken previously to jump up, when it jump back, that energy it will radiate out in the form of the photon, radiation or photon. So this is the this will give the spectrum of the hydrogen atom spectrum. Okay, this will give the hydrogen atom spectrum, right? So if jump back one value it will give, if jump here other value give, if jump here it give the other value. So whole lot of the spectrum of the light will found in the case of the hydrogen also. So what they are, look at that. So see, this is the ground state. This is the ground state, is n equals to 1, n equals to 1. Okay, and n equals to 2 first excited state, 3, 4, 5, 6, 7, 8, like that. Okay, now see what is happening. If any state, from the second state, third, fourth, fifth, sixth, any level, if the electron jump back to the ground state, it will produce the ultraviolet lights. Okay, so what I am saying is, suppose let me draw here the hydrogen atoms levels. This is n equals to 1 level, this is n equals to 2 level, right? This means that this is 1. Okay, this is n equals to 1, this is n equals to 2. I am saying this is 1, this is 2, like that. Okay, for my convenience I am drawing the line. This is n equals to 3, this is n equals to 4, this is n equals to 5. Look at that, what we are learning. N equal to 1 to n equal to 2 is more distance. Then the n equal to 2 to n equal to 3. Then the distance between level will be going decreasing order. Okay, so first and distance between first and second, for example, first and second is greater than distance between second and third, is greater than distance between third and fourth, like that. So any level here, if the electron jump to the ground state, then it will radiate the ultraviolet UV light. Any level to ground state, it will radiate ultraviolet light. Okay, so similarly, now let's see other ones. Okay, so look at that. Second state, visible light, red, blue, green, etc. Okay, so visible light, if any other state to the second state, if it will jump back to second state, then that it will produce the visible light. Okay, same as like the sunlight, red, blue, green, etc. If third, it will produce the infrared. Okay, if the electron jump in the third level, then that is the infrared. So this is the hydrogen spectral lines. Okay, so we will go in the next video, and thank you so much for watching this, and we will go to the next video after this.